Right now, at this exact moment, a machine is moving through space at 37,000 miles per hour. It is not a new machine. It was built before personal computers existed, before the internet existed, before most of the people watching this video were born. It runs on 22 watts of power, less than the bulb above your bathroom sink. It is the most distant human-made object in the history of our species, and it is dying. Not in the abstract, distant way that everything eventually ends. In the specific, measurable, month-by-month way that engineers at NASA's Jet Propulsion Laboratory in Pasadena, California, have been watching for years, tracking the power output, making lists of what to switch off next, deciding which questions will never be answered so that other questions can survive a little longer. In April of this year, they turned off an instrument that had been running almost without interruption since 1977. 49 years. The instrument is called the Low-Energy Charged Particles Experiment. It measured the ions and electrons of interstellar space. It was still working perfectly when they switched it off. They switched it off because they had no choice. And then they attempted something that nobody's ever attempted on, a spacecraft this old, this far away, and this close to the edge of permanent silence. They called it the Big Bang. This is the story of what that means, what is at stake, what it tells us about the universe beyond our solar system, and why the outcome of a procedure happening right now on a 49-year-old spacecraft will determine what kind of signal reaches Earth on the night of November 15th, 2026, a date already locked in the calendar that marks the first moment in the history of human civilization that any object we have ever built will be a full light day from Earth. New here, this channel covers what is actually happening in space, right now with real numbers and real stakes. Subscribe if you haven't yet. You will not want to miss what comes next. Kareem Badaruddin has spent 30 years at JPL. He is a systems engineer by training, a supervisor of chief engineers by role, and the Voyager mission manager by choice. When Suzanne Dodd, JPL's director for the Interplanetary Network Directorate and Voyager's project manager, needed someone to help steer the mission through what she knew would be an increasingly difficult final chapter, Badaruddin did not wait to be asked formally. His words about that decision are worth sitting with. He said, I was just so excited about Voyager, I said, look no further, right? He has one stated personal goal for his role on the mission. He wants to be there for the final transmission, not to celebrate it, to witness it. Because Badaruddin understands something about Voyager that gets lost in the coverage of its records and its discoveries and its golden record, he understands that what is happening to this spacecraft right now is not a slow decline toward an expected end. It is an active engineering problem solved one piece at a time by a small team of people who love a machine that cannot love them back, and that will one day go quiet regardless of how hard they work to keep it talking. On February 27, 2026, a routine roll maneuver caused an unexpected drop in power. The spacecraft adjusted its orientation, the power margins tightened, and the team realized the timeline had moved. The next instrument shutdown, which had been planned but not yet scheduled, was now necessary sooner than anyone wanted. Badaruddin issued the statement that accompanied the April 17th shutdown order. He said, "While shutting down a science instrument is not anybody's preference, it is the best option available." That sentence, measured and professional, carries something underneath it that his other quotes make clear. This is not a bureaucratic decision. This is a man who said he has the best job at JPL, who wanted to be there until the final transmission, watching the instrument list get shorter and the options get fewer, and choosing the words that the press release requires while knowing exactly what is being lost. To understand why the Big Bang procedure matters, you need to understand what Voyager 1 is running on and how close to the edge that margin actually is. When Voyager 1 launched from Cape Canaveral on September 5, 1977, its 3 radioisotope thermoelectric generators produced approximately 470 watts of electrical power. These generators are containers of plutonium-238 that produce heat as the radioactive material slowly decays. That heat is converted into electricity through a process that requires no moving parts, no fuel supply, no maintenance, and no human intervention. They simply decay, and as they decay, the power output falls. 4 watts per year, every year, without exception. After 49 years, the 3 generators now produce approximately 220 watts combined, less than half of what they produced at launch. And of that 220 watts, only a fraction is available for science instruments. The rest goes to keeping the spacecraft warm enough to operate in an environment where the temperature is approximately negative 260 degrees Celsius, 3 degrees above absolute zero, the coldest temperature physically possible in the universe. Turning off heaters to save power risks, allowing fuel lines to freeze, A frozen fuel line means no attitude control. No attitude control means the antenna drifts away from Earth. An antenna pointed away from Earth means silence, not temporary silence. Permanent silence. This is the balance. Badaruddin's team lives inside every single day. The power available for science shrinks. The minimum power needed to keep the spacecraft structurally viable does not shrink. The gap between those two numbers is where all the decisions happen. Of the 10 scientific instruments, Voyager, one carried at launch, 7 have already been switched off. The decisions about which ones to sacrifice were not made in the heat of the moment. The science and engineering teams sat together years in advance and worked out the order which measurements were most critical, which could be lost without destroying the mission's core scientific value, which instruments the spacecraft could afford to lose last. The low-energy charged particles experiment was next on that list. Its principal investigator, Matt Hill at the Johns Hopkins Applied Physics Laboratory, wrote about the shutdown in terms that reveal exactly how the people closest to this mission think about what is happening. So, what does a scientist say when the instrument he has spent his career studying goes dark on a spacecraft 14 hours away by light speed? Hill wrote, "They have a good track record of seeming to perform miracles that stretch the remaining power supply, but eventually this streak will end." Not a protest, not a eulogy, a precise, honest assessment from a scientist who has watched this team perform miracle after miracle and knows with equal precision that the mathematics of radioactive decay does not negotiate. The streak will end. The question is whether it ends before or after Voyager 1 crosses the threshold in November. Which brings us to the Big Bang. The procedure is not a repair. There is nothing broken that can be fixed. The Big Bang is a coordinated restructuring, a simultaneous swap of multiple powered components, replacing older, higher power systems with lower power alternatives that produce less heat but consume less electricity, turning some things off entirely, replacing others with more efficient versions that had not existed when Voyager 1 was designed. The idea is to buy time. If successful, JPL estimates the Big Bang could delay the need to shut off another science instrument by at least 1 year. 1 year of data from the only instrument humanity has ever placed in interstellar space. But the procedure carries real risk. Voyager 1 is 49 years old. Its circuits have been exposed to cosmic radiation for half a century. Some components have already degraded in ways that took the engineering team months to diagnose and work around. Changing how power flows through a system this old at a distance where every command takes 23 hours to arrive and another 23 hours for any response to come back, means that a single unexpected failure mode discovered mid-procedure cannot be corrected in real time. It cannot be corrected in the same day. It might not be correctable at all. This is why the team tested the procedure on Voyager 2 first. Voyager 2 is slightly closer to Earth, carries slightly more available power, and its slightly higher margin makes a potential failure somewhat less catastrophic. Tests on Voyager 2 were scheduled for May and June of 2026. Based on the outcome, the same procedure was planned for Voyager 1 no earlier than July. We are in August. The window when this procedure was scheduled to happen on Voyager 1 has either just passed or is happening now. JPL has not yet published a confirmed outcome. The result of the most consequential engineering operation on the most distant spacecraft ever built is, as of today, unknown to anyone outside the team at Pasadena. There is one additional detail about the LECP shutdown that has received almost no attention. When engineers powered down the instrument, they did not power down all of it. They kept a small half-watt motor running inside the instrument, specifically to preserve the possibility of turning it back on. That is an extraordinary thing to sit with. In a situation where every fraction of a watt is being counted and rationed, the team chose to spend half a watt continuously on the possibility of a future they cannot currently guarantee. If the Big Bang works on Voyager 1, there is a real chance the low-energy charged particles experiment gets turned back on. The instrument that was switched off because the margin was too thin might find itself with a margin again. 49 years of operation, a brief silence, and then if the engineers succeed a return, Badaruddin's words about the mission apply here exactly. The history of assuming things were finished before they actually were has never once aged well on Voyager 1. Here is what Voyager 1 has been finding in interstellar space, and why the data from its remaining instruments is worth the extraordinary effort being made to keep them alive. In 2012, Voyager 1 crossed the heliopause. The heliopause is the physical boundary of our solar system, the point where the solar wind, the stream of charged particles flowing outward from the sun in every direction, finally runs out of energy and gets stopped by the pressure of the interstellar medium pressing inward from outside. Everything inside the heliopause is our solar system. Everything outside it is something else. For decades before any instrument crossed that boundary, scientists had built mathematical models predicting what interstellar space would look like from the inside. The prediction was consistent. A relatively calm, relatively uniform environment, cold, sparse, quiet. The emptiness between stars. Voyager 1 walked into that expected quiet and found a storm. Starting in 2017, the plasma wave instrument began detecting something nobody had anticipated and nobody could immediately explain. A persistent, narrowband emission, an extremely faint but continuous hum in the interstellar plasma that had no counterpart in any model built to describe this environment. Not a one-time signal, not an artifact that could be explained away as instrument noise. A real, consistent signal, year after year, detected across a stretch of space, spanning approximately 10 astronomical units, 10 times the distance from the Earth to the Sunday. Stella Koch-Ocker, a doctoral student at Cornell who was working on Voyager data when this was detected, described it precisely. It's virtually a single tone, and over time we do see it change, but the way the frequency moves around tells us how the density is changing. The paper, published in Nature Astronomy in 2021, described the discovery as the first continuously sampled measurement of interstellar plasma density that humanity has ever obtained. Before this detection, scientists could measure plasma density in interstellar space only when specific events, shocks produced by enormous eruptions from the sun propagating all the way out to the heliopause, triggered brief plasma oscillation, events that the instrument could detect. Those events happened roughly once a year. The gaps between measurements stretched for months. The persistent emission changed that entirely. It converted a sparse, event-driven dataset into a continuous record. What had been isolated data points became a running portrait of interstellar space as Voyager moved through it. And what that portrait is showing, what is being confirmed by every additional day of data from the two remaining instruments, is that the space between stars is not the quiet waiting room the models describe. It has texture, it has weather, it has structure across scales ranging from meters to millions of miles. The interstellar medium is turbulent, variable, and more dynamic than any model built from Earth had correctly predicted. This matters for reasons that extend far beyond pure scientific curiosity. The heliopause is not just a boundary on a diagram, it is a physical shield. The same structure that separates our solar system from the turbulent interstellar environment deflects the most energetic forms of cosmic radiation, the high-energy particles produced by exploded stars throughout the galaxy, from reaching the inner solar system at full strength. If the interstellar environment pressing against that shield from outside is more energetic and more variable than our models assumed, the long-term behavior of the shield itself needs to be reconsidered. We do not yet know exactly what that means for the stability of the heliosphere over geological timescales. We only know, because Voyager 1 told us, that the question needs to be asked. And Voyager 1 is the only instrument we have ever put inside interstellar space to help us answer it. November 15th, 2026. NASA lists the milestone more precisely as Wednesday, November 18th, at 2 hours, 16 minutes, and 7 seconds past midnight Pacific Standard Time. At that moment, Voyager 1 will be 16.1 billion miles from Earth, 25.9 billion kilometers. A signal leaving Earth at that instant will take exactly 24 hours to reach the spacecraft. A reply, if the spacecraft sends one, will take another 24 hours to come home. No human-made object has ever been that far from Earth. Not a single spacecraft in the entire history of our species has crossed this threshold while still transmitting. The Voyager program was designed for a 4-year mission. It is approaching its 50th year, and it will mark this milestone if the Big Bang works, if the power holds. If the antenna stays locked as a functioning scientific instrument, still sending data about a universe that continues to be stranger and more complex than the models built to describe it. The November milestone is not the end. After that date, Voyager 1 will keep moving. 37,000 miles per hour, deeper into interstellar space, every hour getting slightly farther. The communication delay will extend. The power will continue to fall by 4 watts each year. And at some point in the early 2030s, the last instrument will reach the threshold below which it can no longer operate. The last signal will begin its 24-hour journey home. It will arrive, it will be recorded, and there will be nothing after it. Voyager 1 will not stop. There is no friction in interstellar space, no atmosphere, nothing to slow it down. It will keep moving at 37,000 miles per hour through the dark between stars, passing through regions of space that human eyes will not reach for tens of thousands of years. And bolted to its frame, attached to the body of the dying machine, is a gold-coated copper disc, the Voyager Golden Record. It carries greetings in 55 human languages. The sound of rain falling on a forest, the sound of ocean waves, the sound of human laughter. 90 minutes of music from across the full history of human civilization, diagrams explaining the principles of our physics, a map made from pulsar positions showing whoever finds it exactly where in the galaxy our planet sits. Carl Sagan, who helped design it, called it a message in a bottle cast into the cosmic ocean. The record will still be traveling when the sun has become a red giant and swallowed the Earth's orbit. It will still be traveling after every city, every archive, every stone we ever carved our names into has been erased. It is the most permanent thing our civilization has ever made, and it is riding on a spacecraft running on 22 watts. One machine, 22 watts, one chance. The Big Bang procedure is happening now. The result is not yet public. What we know is that the team at JPL is doing what they have always done, choosing the harder option, accepting the risk, and keeping the mission alive for one more year, one more instrument, one more transmission from the only piece of human technology that has ever been where Voyager 1 is right now. The signal is still coming. 23 hours to arrive, carrying information about a universe that keeps turning out to be more extraordinary than any model built from Earth has correctly described. When JPL confirms what happened with the Big Bang, whether the procedure worked on Voyager 1, whether the low-energy charged particles experiment is back online, whether the November milestone will be crossed by a spacecraft with more capability than it has today, we will cover it on this channel. Subscribe. That update matters.